In order to find the magnetic field of a current loop, we need to establish a coordinate system wherein we can cancel out the y components of the magnetic field, and so that we are left only with the z components. So we have here a current loop with a current moving in the counterclockwise direction. We've placed it in the xy plane so that the magnetic field is directed entirely in the z direction when the y components cancel out, as seen over here. So we know that the current in the z direction is equal to the current, or the magnetic field, excuse me, times cosine phi, which is this angle here, which is the same as here. So we are taking only the z component of the magnetic field that we are evaluating from these two opposite parts of the current loop, K and J. So using the Biot-Savart law again, which states mu naught over 4 pi times I delta S, and in this instance we're going to be looking at segment K, so delta SK times R hat, or cross product R hat, over R squared, then multiplied by cosine phi in order to just get the z component. So now we can start substituting some terms. So the cross product of delta SK times our product, we have delta SK in this direction here, and our R hat pointed towards the point we are trying to evaluate the magnetic field at. So the cross product is equal to delta S times 1 times sine 90 degrees, which, since the sine of 90 degrees is 1, yields just delta S. So plugging that back into the equation, we get mu naught over 4 pi I delta S over R squared cosine phi. Now for the value of R, which is this distance here, is equal to the square root of capital R, which is the radius of the current loop, times z squared, which is the distance from the center of the loop to the point we are trying to evaluate the magnetic field at. So R is the square root of radius squared plus z squared. Now in the equation, the value of R is squared, so the square root disappears, so we are left with mu naught over 4 pi I delta S over R squared plus z squared cosine phi. Now to evaluate cosine phi, the angle phi is the same as that between the magnetic field of B and the z component of B, which is the same as this angle here between R hat and the radius. So cosine, which is adjacent over hypotenuse, is equal to the radius over R, which, since having determined the value of R in the previous step, we can plug in R over root R squared plus z squared, and then we can return that to the equation. So we now have mu naught over 4 pi times I delta S over r squared plus z squared times r over root r squared plus z squared. Now you can combine like terms, and you are left with mu naught over 4 pi I delta s r over r squared plus z squared to the 3/2 power. So this tells us the magnitude of the magnetic field in the z direction for this current loop. Now, in order to evaluate the magnetic field for the entire loop, since this is only the portion from k and j, we need to integrate this answer. So, the magnetic field of the entire loop is equal to the integral of mu naught over 4 pi I delta s r over r squared plus z squared to the 3/2. Now in this integral, the delta s becomes our ds, and since all of these terms are constant in this problem, the current remains constant, the radius of the loop remains constant, and the distance from the center of the loop to the point we are evaluating the magnetic field at is constant, all of these terms will be pulled out of the integral, so that we are left with only mu naught over 4 pi IR over r squared plus z squared to the 3/2 integral of ds. And in order to determine ds, ds is representing here the circumference of the loop, or like basically the length of the loop. So since the circumference of a circle equals 2 pi r, and the radius of our loop here is capital R, 2 pi r is equal to the s. So you get mu naught over 4 pi IR over r squared plus z squared to 3/2 times 2 pi r, which you can then simplify to mu naught I r squared over 2 r squared plus z squared to the 3/2. And that tells us the magnitude of the magnetic field of this current loop, and we have already determined that it is directed in the positive z direction.